The hardened resist is then removed in a dry process, using oxygen plasma, which may include fluorine, followed by hot acid baths. This leaves a stenciled silicon dioxide layer as insulation. Photolithography will be used with each of the subsequent masks in the process. This technique allows us to isolate microscopic regions of the wafer and construct them into components of the electronic circuit. In this way, the transistors and circuits are gradually built, a layer at a time. In the ion implanter, dopant ions will bombard the wafers to create N-type regions. The depth of the ion implantation depends on the amount of energy used. Dopant ions are separated from other elements and accelerated to high velocities in a strong electric field. The ions are then driven into the wafers, implanting the exposed silicon regions. The silicon dioxide layer on the wafer blocks the dopants from unwanted regions. Because these wafers are P-type, phosphorus ions, which are N-type dopants, are implanted. Exposing the wafers to high temperatures diffuses the ions deep into the silicon substrate. This creates a well of N-type substrate where the P-channel transistor will be built. If the wafers were N-type, then boron would have been implanted to create P-wells. A new thinner layer of silicon dioxide is regrown, and its thickness is carefully monitored and measured. In a deposition furnace, a layer of silicon nitride is deposited over the oxide layer. The nitride layer prevents additional growth of the silicon dioxide layer and protects the region where the transistors will be built. Photoresist is again evenly spread on the wafer and baked in preparation for the next mask. Using a computerized machine, each new mask is perfectly aligned to the pattern already on the wafer. The second mask, used to define the actual transistor regions, is also exposed across the surface of the wafer. The wafers are developed to remove the exposed photoresist, then rinsed and baked. The wafers are then plasma etched. The free fluorine atoms react with the exposed nitride. After the photoresist is removed, the wafers go back into the oxidation furnace. A thick insulating layer of silicon dioxide, known as field oxide, will be grown where the nitride has been etched. To grow these thick layers of oxide, oxygen combined with hydrogen is introduced on the wafers as steam. This insulation reduces the electric fields between the surface and the underlying regions. Through the microscope, the field oxide looks like white boundaries. It will block the current from leaking between devices, allowing thousands of transistors to coexist in a small area. The remaining nitride layer is then removed by a combination of dry and wet etching. The wafers are then implanted with boron ions, which penetrate the silicon substrate only through the thin oxide layer. This provides uniform electrical characteristics in the regions where the transistors will be built. This thin oxide, which may have been damaged by the implantation process, is removed, and a new layer of silicon dioxide is grown in the gate area. In the vertical furnace, the gate electrodes will be formed by depositing polysilicon. Polysilicon consists of many small grains of silicon, which will be doped with phosphorus, an N-type dopant, to make them more conductive. With photolithography and the next mask, the polysilicon layer will be etched to create the gate electrodes that turn transistors on or off. To carefully control this etch step, the polysilicon is dry etched. The width of these gates determine the distance that separates the source from the drain of the transistor, and ultimately the speed of the circuit. The remaining photoresist is removed once again. The gates become the first conductive layer connecting to different transistors. Mask number 4 allows the implantation of the N-channel regions with a high concentration of N-type dopants to form the highly conductive source and drain regions of the N-channel transistors. Mask number 5 uncovers regions in the P-channel transistor, which are implanted with a high concentration of boron, a P-type dopant, to create the source and drain regions of the transistor. The photoresist is stripped, and again, the wafers are cleaned. In a furnace, the wafers are annealed, and defects created by ion implantation are repaired. Next, a thick insulating glass layer is deposited. The many different layers previously deposited and patterned are completely covered, leaving an unleveled glass surface with varying depths of fields. To ensure every part of subsequent mask patterns are transferred in sharp focus, the surface must be planarized.